Okay, Chapter 25, Section 2 is on motional EMF, or EMF, electromotive force, or something akin to voltage separation, which is produced by motion, motional EMF. And we're going to start by first considering a very easy way of producing an EMF in a magnetic field, and that is to take a metal conductor like the bar that's depicted here in the figure. And if it's a conductor, the charges on the inside of that conductor are free to move. So as I pull the entire bar to the right, all of those charges which are riding along with the bar are moving with respect to the magnetic field, which is drawn into the page by the x's. So as the bar moves to the right, the plus charges, which we normally associate with electric current, begin to move upward by the force that they experience moving to the right in a magnetic field that is pointing into the page. And you should use your right-hand rule to verify that the velocity and the magnetic field are pointed in such a direction as to result in a force upward. Now, the force, the magnetic force on the charges, the charge carriers inside the metal experience a force equal to QVB. Remember, the force on an individual charge moving at velocity v through a magnetic field B is QVB. So the force on each charge carrier is QVB. Positive charges therefore move upward. And at the same time, as the plus charges move up, we can envision that negative charges move down. In reality, the electrons move down to the bottom in such a way as to leave several ions at the top. And so it still ends up with plus charges on the top and electrons on the bottom if the only charge carriers are electrons. So we can imagine that we have, well, it is true that we have a net positive charge on the top of the bar and a net negative charge on the bottom when we move the bar to the right, as shown in this diagram. Now, as those charges separate, they themselves start producing an electric field, and that electric field builds up inside the bar as it moves to the right in the magnetic field. It moves very quickly to establish an equilibrium value, which happens when all the charges stop moving. And we have a net positive charge on the top and a net negative charge on the bottom when that happens. So why does it stop at all? Why doesn't the charge continue separating? Well, that's because the forces that are driving the charges up in the case of positives and down in the case of negatives, because they're moving through the magnetic field, will be met with an equal and opposite force on them from the electric field that they produce. So the electric field that they produce will eventually become large enough to cancel the force of the magnetic force which is separating the charges, and they will reach an equilibrium where those two forces are balanced with one another. So let's look at the electric force first. The electric force on each of the charges in the vicinity of an electric field E is going to be equal to QE. The charge multiplied by the electric field gives rise to the force that it experiences. It also experiences a magnetic force because the bar is moving through the field, FB, which turns out to be QVB. So ultimately, the charges move under the influence of the magnetic field until they produce a big enough electric field that cancels the force of the magnetic field on those moving charges. And so the important pieces of this equation to look at are right here. QE is equal, therefore, to QVB when this balance occurs. When FE, the electric force, is equal to the magnetic force, then QE is equal to QVB. We can divide out a common factor of Q, and we find that the electric field that exists inside the metal when equilibrium is established is equal to the velocity of the motion of the bar times the magnetic field. Okay, so because this electric field exists inside the bar, there is therefore a voltage difference between the top and the bottom of the bar. And because of the relationship between voltage and electric field, we can calculate the voltage potential difference from the top to the bottom of the bar as equal to VLB, the velocity of the bar times its length times the magnetic field strength B. This gives us a way of calculating the the total voltage difference across that bar. Because we can calculate the electric field that exists inside the bar when everything is balanced, knowing that it cancels the magnetic force, we can therefore calculate the voltage difference between the two ends, since the voltage difference between the ends is related to the electric field with a proportionality constant equal to the length of the bar. So we can therefore calculate that the voltage difference across the length of the bar is equal to VLB, where little v is the velocity with which the bar moves, L is its length, and B is the magnetic field strength. And therefore, the potential difference which is induced by moving a bar through the magnetic field is, its strength depends on the magnetic field and the speed of the moving through the field. If we increase the speed of the bar, that increases the voltage difference between the ends, since the two are linearly proportional as seen in that equation. Likewise, if we adjust the strength of the magnetic field, the voltage will accordingly adjust linearly as well. Okay, so we have a general principle then that the EMF generated by moving a bar through a magnetic field is equal to the velocity at which it moves times its length times the magnetic field strength. The question arises, could we potentially use this as a battery? Well, it wouldn't be a very good battery because the only time it has the plus and minus charges separated is when it's moving, so you need something to make it move in order to turn it into a battery. But we could imagine a scenario where it can form a type of battery and generate current. For example, the figure on the right shows a large loop of wire and a bar resting on those two legs of that wire, and the bar is metal, the wire is metal, and therefore when the bar lays on top of the metal, as it does here, we see that the arrangement forms a closed circuit because the rest of this circuit, which goes around, forms a closed loop through which current can move. So, as the bar is moved along the track, we see that, as we understand before, the positive and negative charges are going to separate to two ends of the bar, but this time they're not going to stop. They're actually going to generate a current which moves in the counterclockwise direction as shown around this loop. So as long as the bar is moving, there is a charge separation induced by the magnetic force which causes a current to flow around the loop. And the current will continue flowing as long as the bar is moving. But as we're going to find, it's not going to move on its own. In fact, it requires a force to pull the bar along because it is generating electric current, and the energy for that current is coming from the energy supplied by whoever's pulling the bar. So the EMF that exists between the two ends of the bar can drive a current in a closed loop for a situation that's depicted here, for example. We can actually turn it into a type of battery and generate current just by moving a bar inside of a magnetic field. Okay, so as we've said, this acts kind of like a battery, supplying a separation of charge that can potentially drive current around a circuit if a closed circuit is available. And we call this current induced because it's not being supplied by something that's pushing charge into the circuit. It's actually being induced by motion through a magnetic field. That induced current that results from the moving bar in the magnetic field is the type of current that exists when we have this kind of conversion. In this particular case, we're turning the energy of motion into the energy of an electric circuit. And so in some sense, you can say that the real battery is whatever provides the force to pull this bar along. Okay, so let's apply Ohm's law to this situation, in which case we can calculate the current that moves through this circuit if we know the EMF, which we just calculated, and if we know the resistance of the circuit R. So whatever resistance exists in both the coil or the loop of wire, the U-shaped piece of wire, and the bar that's moving through it, the total resistance of the circuit will depend on those two components in the circuit. And so if we can measure what that resistance is, then we can calculate the current that moves through the circuit, which is VLB over R. The velocity with which the bar moves times its length times the magnetic field strength divided by capital R, which in this case is the resistance in the circuit. Okay, so let's see if we can learn a little bit more about the force required to move this bar. From chapter 24, we learned that when you have a piece of wire carrying a current I, and it's immersed in a magnetic field, the force on that piece of wire is ILB. I, the current it carries, L, the length, and B, the strength of the magnetic field. This is when it's carrying current perpendicular to the magnetic field lines. So that's the force that is exerted on any current-carrying wire. This piece of the circuit, the bar, is actually a piece of wire on which there is a magnetic force. It's carrying current I, which we just calculated on the previous slide, and it's moving through the magnetic field. But the force itself, which is the force of the magnetic field on the current, is equal to ILB, and that's going to be equal and opposite to the force required to pull this bar. If we're pulling it along at constant velocity, that means that both forces exactly balance one another, and therefore we can calculate how strongly we need to pull the bar by knowing what the magnetic force on that current is. Therefore, we can calculate the force of the pull, which here is equivalent to the force that the magnetic field applies on the current, the length of current in the bar. And then we can replace I with what we calculated on the previous page to find that the strength of the pull required to move the bar at velocity v is equal to VL squared B squared over R. V is the velocity at which it moves, L is its length, B is the magnetic field strength, and R is the resistance of the entire circuit. So the resistance here is going to be the resistance of the wire loop as well as the bar. They will total to a complete resistance for the circuit, which then can be used to calculate the force of the pull. Also from last semester, we learned that the power that a force applied at velocity v gives is equal to the force of the pull times the velocity. The power done by that force in pulling something at velocity v is equal to the product F pull times v. If we take F pull from up here and plug it in down here, then we find that the power, whoops, sorry about that, we find that the power, the power expended by the force which is pulling this bar along is equal to V squared L squared B squared over R. Now, where does that power actually go? We learned about energy conservation last semester, and we know that energy is neither created nor destroyed, so somehow we need to account for the power that is put into the circuit by the pulling hand, and the only place it can go ultimately is in dissipated heat in the circuit itself. This circuit doesn't do anything. It doesn't light any bulbs, it doesn't run any engines, it simply goes around in a circle and it's dissipated in the form of heat because the circuit has a finite resistance R. Well, that power dissipated, we learned before, is the current squared times the resistance in the circuit. So if I take the current from the previous page and square it and multiply it by the resistance, I get that the power dissipated in the wire for a bar moving at velocity v of length L in a magnetic field strength B with total resistance R is equal to V squared L squared B squared over R, which is the same as the power delivered by the pull. So we see that energy is conserved here. The power delivered by the hand pulling the bar is exactly turns into the power that is dissipated in the wire as heat. And the two approach from slightly different vantage points or starting points show that they're equal to the same number. Okay, so this is the principle upon which generators are designed. The principle that a moving wire, a wire that moves through a magnetic field, can have a current induced in it. Here you see a simple design of a kind of a generator. In this particular case, the loop is formed into a rectangle connected to a long pair of shafts, which allows the entire loop to rotate in a circle inside this magnetic field. Now you'll notice that the direction of the field is to the right, okay, and the loop is oriented in such a way, that this left rail right here, just prior to the time that this figure is being depicted, was down lower, and as it moves up through that magnetic field, we have a current that is generated in it into the page, as is shown by this figure. Let's just make sure we agree with that. Okay? So when this part of the loop right here was a little bit lower to the left and it was coming up through the field, its direction was up, which is the velocity v, so v is up, and b is to the right. Oops, sorry about that. B is to the right. And so using our right hand, we can figure out that with motion up and field to the right, the force is going to be, according to the direction of our right thumb, into the page for the left side of the coil. Now look at the right side. Just previous to where it's depicted here, it was moving down through that field. And if you do the same kind of right-hand rule, you'll find out that with downward motion through a field pointing to the right, the current is coming out of the page at the bottom. But you'll also notice that, as depicted, if we move forward in time, the part of the bar that used to be on the left will now be on the right, and therefore each of those two segments, the left and the right segment, will experience alternating current. When they're moving up to the left, on the left side moving up to the field, the current is into the page, and the right side at the same time is out of the page. So there's a loop, a current that moves around that loop in a clockwise fashion as seen by us. But as soon as the loop is halfway around from there, it's now moving such that the one that was moving up through the field is now moving down, and the side of the loop that was moving down is now moving up. And so the net result of that is that the current induced inside that loop is alternating. It alternates through one complete cycle from 0 to a max, 0 back down to a min, and back to a max in the course of moving or rotating once through the magnetic field. So just by moving this coil in a continuous fashion around and around and around in this magnetic field, we can generate a current of alternating value. It's a current that sloshes back and forth in a way that we haven't seen yet. We've only looked at DC current in simple circuits, but we will soon talk about alternating currents. Okay, and the value of current, or the current itself, can be tapped from those two halves of the loop right here into a circuit that moves around and has resistance R and dissipates that energy or uses it for the purpose of driving an engine or something else. Okay, so the metal rings that are on each one of those shafts rub up against a brush, which allows us to pull the current off of that and move it into the circuit. Okay, so there are a lot of good examples in modern life where this kind of induced current is used to good advantage. And one of the technologies I'd like to point out here is the technology of energy production from wind. The wind drives these turbines around in a circle, and inside the housing at the top of one of these, which you see right here, you can see a human being to get a size of the scale of these things. When we see them from the roadside, they tend to look smaller way up high than they actually are, but these are enormous devices. The blades alone are 120 feet long each, so that from the ground to the very top of this particular sail, it's about 320 feet or so. Okay, so this machine, or this generator, works on the basis of rotation of the shaft being turned into energy by a mechanism that we just basically considered, that of a rotating coil, inside a magnetic field. So inside the housing at the top of this wind generator, this wind turbine, there is, oh gosh, sorry about that, there is a large shaft which rotates a coil inside a very large magnet and generates current, which can then be sent to the ground and tapped out to various places and used. These actually generate a lot of power each. It's really quite remarkable. But when you're talking about a structure this big, you can imagine the power of the wind that it takes even to drive these things, as heavy as they are. But when wind does drive it, it generates alternating current by virtue of this very simple concept of rotating a coil inside a magnetic field.